Today we are going to learn third topic, that is sets and functions. Sets and functions. Sets and functions. First we define set. Set is collection of well-defined objects. A set is collection of well-defined objects. The objects in the set are called elements or points. A set is collection of well-defined object. A set is collection of well-defined objects. The objects in the set are called elements. Or points. For example, the sets are denoted by capital letters, capital A, capital B, capital C, or capital P, capital Q, capital R, and objects or elements or points are denoted by small letters, small a, small b, small c, and so on. For example, number 1, capital A is equal to set of 1, 2, 3, and so on up to 10. This is finite set. Second, capital B is set of small p, small q, small r, small s. 3, C is equal to 1, 2, 3. 3 numbers. The sets are denoted by capital letters and elements are denoted by small letters. If B is the elements of set A, then we write B belongs to A. If B is not element of A, then we write B does not belongs to A. If B is the element of the set capital A, then we write B belongs to set A. B belongs to set A. If B is not an element of element of set A, then we write small b does not belongs to A. Small b does not belongs to set A. Now we take some problems. Describe the following sets of real numbers geometrically. Example, describe the following sets. The following sets of real numbers. Real numbers geometrically. Number first, capital A is equal to set of all x such that x is less than 7. Second one, capital B is set of all x such that mod x is greater than or equal to 2. Third one, capital C is set of all x such that mod x is equal to 1. We describe these three sets. Solution. Since capital A is set of all x such that x is less than 7. On real line, all elements, all numbers, this is say 0, 2, 4, 6 and 8. Here is 7. Set of all x such that x is less than 7, not equal to also 7. Therefore, 2, 4, 6, 8. Here is 7. All elements less than 7 are present on LHS of 7 except 7. Here is -2, -4, -6 and so on. All the elements less than 7 lies on this real line. Lies on LHS of 7. These are the elements whose set is denoted by capital A. Set of all x such that x is less than 7. Second one. There is second. Since capital B is set of all x such that mod x is greater than or equal to 2. Mod x is greater than or equal to 2. The elements of this set capital B are on the real line. Here is -2, origin, -2. Here is +2. All the elements greater than or equal to 2. All the elements greater than or equal to 2 and all the elements whose values are less than or equal to -2. Less than or equal to -2. This is the set of all x such that mod x is greater than or equal to 2. If we take mod of minus 2, we will obtain 2. Mod of minus 3 is also greater than 2, and so on. That is, we eliminate set of real number R minus open interval minus 2 to plus 2. We remove the points from minus 2 to plus 2, open interval minus 2 to plus 2. Third one. Since capital C is the set of all x such that mod x equals 1. Mod x is equal to 1. Equal to 1. Therefore, we have only 2 points whose modulus is equal to 1. Whose modulus is equal to plus 1. This is say 0. Here is plus 1 and minus 1. Plus 1 and minus 1. Plus 1. Capital C is set of all x such that mod x is equal to 1 is equal to only 2 points minus 1 and plus 1. Capital C contains set of all x such that mod x is equal to 1. This means x is equal to minus 1 and x is equal to plus 1. That is, whose modulus is equal to plus 1. Plus 1. These sets are denoted. First set, capital A, capital B, capital C are denoted geometrically. Second example. Describe the following sets of points in the plane geometrically. Describe the following sets of points. The following sets of points. Sets of points in the plane geometrically. In the plane geometrically. Geometrically. Number 1, capital A is set of all xy such that x square plus y square is equal to 1. Second one, capital B is set of all xy, order pair xy, such that x is less than or equal to y. Third one, capital C is set of ordered pair xy such that x plus y is equal to 2. X plus y is equal to 2. Solution. Number 1, capital A is, since capital A is set of all ordered pair xy such that x square plus y square is equal to 1. X square plus y square is equal to 1 is the circle with center at origin and radius is equal to 1. Set of all points on the circle whose center is at origin 0, 0 and radius is equal to 1. This is x square plus y square is equal to 1. All points which lies on the circle, x square plus y square is equal to 1 is set of all points which lies on this circle. X square plus y square is equal to 1. Capital B. Number 2. Since capital B is equal to set of all xy such that x is less than or equal to y. X is less than or equal to y. All points whose value x is less than or equal to y. X is less than or equal to y. X-axis, this is y-axis, origin O, y is equal to x or x is equal to y. X is equal to y, y is equal to x. This set of points x less than or equal to y, that is x is equal to y, lies on this line. This is origin O. X is equal to y. X is less than y. X is less than y. If we take here 0, 5, 0 is less than 5. 3, 7, 3 is less than 7, and so on. All points on the line and above this line. All points which lies in this region are included in set B. X less equals y. X is equal to y. X is equal to y. Third one. C is set of all points such that x plus y is equal to 2. Third one. Since capital C is equal to ordered pair xy such that x plus y is equal to 2. X plus y is equal to 2. Ordered pair xy such that x plus y is equal to 2. All points which lies on this line, x plus y is equal to 2. All points, all set of points which lies on x plus y is equal to 2. Y-axis, this is x-axis, origin, this is 1, 2. Here is 1 and 2. 2, 1 and 2. When x is equal to 0, we obtain y is equal to 2. That is this point. When x is equal to 0, y is equal to 2. Y is equal to 0, we obtain x is equal to 2. This is 2, 0. And this straight line, this straight line this set of points which lies on this line x plus y is equal to 2 is the set capital C. Capital C is set of all points which lies on this line. Lies on this line. This is x-axis, this is y-axis. C is set of all xy such that x plus y is equal to 2. X plus y is equal to 2. Operations on sets. First operation is union. If A and B are two sets, then A union B is the set of all points either in A or in B or both. Symbolically, we define A union B is equal to set of all x such that x is in A or x is in B. Either x is in A or x is in B or both. Operations on sets. Operations on sets. Operations on sets. First definition is union. If A and B are two sets, if capital A and capital B are two sets, then A union B, A union B is the set of all elements, either in A or in B or both. Symbolically, we write capital A union B is equal to set of all x such that x belongs to A or x belongs to B. X belongs to A or x belongs to B. For example, capital A is equal to 1, 2, 3. Capital B is equal to 3, 4, 5. Then A union B. A union B is equal to 1, 2, 3, 4, 5. All elements from the set A and from the set B. Capital A union B. A union B. This is operation, union operation. Now we define intersection operation. If A and B are two sets, then A intersection B is the set of all points in X and X belongs to A and X belongs to B. Symbolically, we write A intersection B is equal to set of all X such that X belongs to A and X belongs to B. X belongs to A or X belongs to B. Definition. If A and B are two sets, capital A and B are two sets, then A intersection B is the set of all elements, in both A and B, in both capital A and capital B. Symbolically, we define A intersection B is equal to set of all X such that X belongs to A and X belongs to B. If the elements X is in A and in B, then we take the element X is in A intersection B. For example, if capital A is equal to 1, 2, 3, capital B is equal to 3, 4 and say 6, then A intersection B is the singleton element 3. Since 3 belongs to A and 3 belongs to B, therefore 3 belongs to A intersection B. We define empty set. Empty set is the set denoted by phi, and the set which has no element. The set which has no element is called empty set. Empty set. The set which has no element is called empty set. Empty set is denoted by Greek letter phi or only curly bracket. Empty set. We define empty set. Empty set denoted by phi. Denoted by Greek letter phi. As the set which has no element. The set which has no element is called empty set. For example, capital A is equal to 1, 3, 5. Capital B is the set 2, 4, 6. Then A intersection B is equal to 5. Is equal to 5, empty set. There is no common element either in A or in B. A intersection B is equal to empty set 5, or this is also notation for empty set. Empty set. Now we define A, B minus A. If A and B are two sets, then B minus A is defined as B minus A is equal to set of all x such that x is in B but not in A. But not in A. Definition. If A and B are two sets, if capital A and capital B are two sets, then we define capital B minus A as B minus A is set of all x such that x belongs to B but x is not in A. X is not in A. For example, capital A is equal to A small p, small q, small r. Capital B is equal to small a, b, c, p, q and r. Then B minus A is equal to small a, small b, small c. X is in B but not in A. But not in A. That is B minus A. Set B minus A. If A and B are two sets and every element of A is the element of B, then we say that A is subset of B, or B contains A, or B contains A. B minus A. X belongs to B, but X is not in A. X is not in A. That is B minus A. X belongs to B, but X is not in A. That is B minus A. And we are two sets. B minus A is set of all x such that x is in B, but not in A. But not in A. Since P, Q, R are three elements present in B, but not A, B, C are three elements. They are present in B, but not in A. Therefore, B minus A contains only three elements A, B, and C. Set of all x such that x is in B, but not in A. But not in A. X does not belong to A. Another definition. If every element of a set A, if every element of set A is an element of set B. Is an element of set B. Of set B. Then we write A is subset of B, or B contains A. B contains A. A is subset of B, or B contains A. Every element of A is an element of B, then we write A is subset of B, or B contains A. For example, capital A is equal to 1, 3, 5, 7. Capital B is set of all 1, 2, 3, 5, 6, 7. Each element of A, 1 is there, 3 is also there, 5 is there, 6 is there. Therefore, every element of A is an element of B, therefore A is subset of B. A is subset of B. A is subset of B. Or B contains A. B contains A. B is in A. B contains A. Another definition. We say that two sets are equal if they contains precisely same element. Two sets, we say that two sets are equal if they contains precisely same element. And we write A is equal to B. A is equal to B if and only if A is subset of B and B is subset of A. For example, A is equal to 1 small a, B 3. B is equal to 1, 3, A and B. Then we write capital A is equal to B. 1 is there, 3 is there, A is there, B is also there. Therefore, A is equal to B. Each element of A is in B. That is, A is subset of B. B is also subset of A. Therefore, A is equal to B. We note that capital A is equal to B if and only if capital A is subset of B and B is subset of A. B is subset of A. That is, B contains A and A contains B, then A is equal to B. A is equal to B if and only if A is subset of B and B is subset of A. Now we see the theorem. If A and B are subsets of S, if capital A and B are subsets subsets of capital S. Capital S is big set, that is universal set. A is subset of S, B is also subset of S. That is, S contains both the sets A and B. Then show that, then prove that A union B bracket dash, A union B bracket dash, that is complement of union A and B, is equal to A complement intersection B complement. A union B bracket dash is equal to A dash intersection B dash, A dash intersection B dash. A is equal to B if and only if A is subset of B and B is subset of A. Proof. Suppose X belongs to capital A union B bracket dash. This implies X does not belongs to A union B. This implies X does not belongs to A or X does not belongs to B. This implies X belongs to A dash and X belongs to B dash. This implies X belongs to A dash intersection B dash. Hence, A union B bracket dash is subset of A dash intersection B dash. We have proved A union B bracket dash is subset of A dash intersection B dash. Conversely, suppose Y belongs to, Y is an element of A dash intersection B dash. This implies Y belongs to A dash and Y belongs to B dash. Y is in A dash and Y is in B dash. This implies Y does not belongs to A and Y does not belongs to B. Y does not belongs to A dash. Y belongs to A dash. This means Y does not belongs to A or Y does not belongs to B dash. Y does not belongs to B. This implies Y does not belongs to A union B. This implies Y belongs to A union B bracket dash. Therefore, A dash intersection B dash is subset of A union B bracket dash. This is say result number 1. This is say result number 2. From 1 and 2, from 1 and 2, we write A union B bracket dash is equal to A dash intersection B dash. Hence the proof of this theorem. Similarly, we can prove that theorem second, that is, if A and B are subsets of S, A and B are subsets of yes, then A intersection B bracket dash, A intersection B bracket dash is equal to A dash union B dash. On the same way, we can prove this theorem second. Thank you for watching the video.